Math 104, we're working on the second part of section 1.7, absolute value inequalities. So when packaging food, the actual weight or volume of the contents has to be close to the amount printed on the box. So if the weight of a breakfast cereal in a box must be within 3% of the printed weight, 20 ounces, what is the acceptable range of weights? So these are the types of questions we'll be able to solve at the end of this lesson. Please start with a warm-up. So like we saw yesterday, we're going to take this, and since the absolute value is isolated, we can split it up into two equations. One of them, the equation without the absolute value bars, and one of them set equal to the opposite of the other side. So we get x equals 9, and x equals -3. Now one way to interpret this is of what's known as a transformed function. We've taken the regular absolute value function, that V-shaped graph, and we've moved it over. We've actually moved it over 3 to the right. And now, instead of being centered at 0, we're centered at 3. So 3 is the center of this. And the 2 points then, here's the distance. So 3 gives us the center, and 6 gives us the distance. Now, when we just did regular absolute values, kind of like this, we were talking about the distance from 0. Now we're talking about the distance from 3. So the 2 points are 6 away from 3. So we start at 3 and move 6. 1, 2, 3, 4, 5, 6 to the right, and we get 9. And 3, 1, 2, 3, 4, 5, 6 to the left, and get -3. But what if we want to talk about not just those 2 points, but all points that are within 6 of 3. All right, then we use an absolute value inequality. So instead of the equal sign, now we've got the inequality. So this means the distance is less than 6 from 3. So that includes all points in between. So that's the difference between solving absolute value equations and inequalities. With inequalities, we're going to get a set like this. So there are 4 different situations that come up with absolute value inequality. And these graphs should look familiar from yesterday, basically the same types of graphs. So let's look at this first one. Let's say we have the absolute value of x is greater than 2. So thinking in terms of distance from 0, this means that it's all points that are greater than 2 away from 0. So that means x is less than -2 or x is greater than 2. So that makes the solution sets. Now this is what we worked on yesterday, going from compound inequalities like this to the solution set in the graph. So we'll be doing a little bit of review of yesterday. All right, so from this follows that the solution set is -infinity to -2 unioned with 2 to infinity. So we've got this part here represented here and this part represented here. And then the graph is the split graph, and it's all points. If this is 0, we have to be at least 2 units away from 0, so that's everything on the outside. And then this is just a different version of it with greater than or equal to. So everything follows from that, greater than or equal to or less than or equal to here. And then since we have greater than or less than or equal to, we have the brackets instead of parentheses, and the same thing here. But other than that, everything's the same. All right, now this is less than 2, so this means all points that are within 2 of 0. So that means everything from -2 to 2. And then translating this into interval form, we got -2 to 2 in interval form, using parentheses because we have just less than. And then here's our graph that corresponds with that, every point between -2 and 2. And then here's the less than or equal to version of that, so everything's the same except for we're doing less than or equal to. And then the brackets instead of the parentheses. So this is the 4 situations. So it really helps to think in terms of distance from 0. Now in solving absolute value inequalities, step 1, we're going to isolate the absolute value. So you can see with these, the absolute value is already isolated with all these, but we may need to isolate it. Now we're going to rewrite the absolute value inequality as an equivalent compound inequality. So when you see this, we're going to go from this step to here. So that's always going to be the first step, is to write a compound inequality. Now, when you have the absolute value is greater than the number, then it turns into an OR inequality, because we're talking about points that are at least 2 away from 0. Same thing here. This is greater than the number, so it's an OR inequality. Now, this means within 2 of 0. So when you have the absolute value is less than 2, that becomes an AND inequality. And this is just another way of writing an AND inequality. You can solve it as a 3-part inequality. So you're not necessarily going to see the word AND there. You just have to realize that a 3-part inequality is an AND inequality. Because both of these parts have to be true. X has to be greater than -2, and x has to be less than 2. And same thing here, except we have less than or equal to. So this is the absolute value is less than the number. So we have an AND inequality. So that's the first thing you need to be able to recognize, is which type we have. And then we're going to solve the compound inequalities, write the answer in interval notation, and graph. So first example, we're going to solve absolute value of x minus 3 is less than 4. All right, so the absolute value is less than the number. So this is an AND inequality. So the way to write this is we're going to take the negative of this number, put it to the left. So -4 is less than. Oops. When we write it, remove the absolute value. So we got x minus 3 in the middle and less than 4. Now we can solve this 3-part inequality. I'm going to add 3 to each part. Just remember to add to all 3 parts. And that gives us -1 is less than x is less than 7. Now we can write this using interval notation. Same numbers. We have strictly less than, so we're going to use parentheses. -1 to 7. And then graph it using the same symbols and shade in between. Now with these, where we don't have a coefficient on the x, you can do a quick check here. All right, 3 is the center. We have to be within 4. So 3, 4, 5, 6, 7, 4 places the number 7, and 3, 2, 1, 0, -1. So 4 units to -1. So that works. It only works with the simpler ones then. Once we start getting a coefficient in there, then it changes everything. Your turn, number 1. All right, so we got our inequality is less than 3. So we can turn this into an AND inequality. -3, less than or equal to, x plus 7, less than or equal to 3. All right, now we got to get rid of that 7, so I'm going to subtract that from all 3 parts. And it gives us between -10 and -4. All right, now we'll write this using interval notation. -10 with a bracket because of less than or equal to. and a negative 4, and then the graph. And it's all points in between. Next example. We got absolute value of x plus 5 is greater than or equal to 2. So in this case, we've got the absolute value is greater than the number. So this turns into an OR inequality. All right, we've got the equation without the absolute value bars. Everything else is the same. Or x plus 5. And here's where we have to be careful. Now, when doing the second one, we have to do two things. We have to switch the direction of the inequality. So it becomes less than or equal to. And then make the value the opposite. Turn it into negative 2. And now we can solve. So we got x greater than or equal to negative 3. And x is less than or equal to negative 7. And still got an OR in here. All right, so we got less than or equal to negative 7, so that's going to be negative infinity here. To negative 7, we got less than or equal to, so we got the bracket. Union. And here we got x greater than or equal to negative 3. So we got a bracket for greater than or equal to. Negative 3 to infinity. And the graph then will be one of those split graphs. We got negative 7 this way. We'll have the bracket, same symbol as in interval notation, and all the way to the left. And then a negative 3 over here, and we'll do a bracket, and all the way to the right. Your turn, number 2. Just a reminder, make sure you're pausing the video to do the your turns. A very important part of the learning process. All right, we got absolute value greater than the number, so this is an OR inequality. So do x minus 2 is greater than 4. And then the other equation will be x minus 2. Switch the sign and make the number the opposite. All right, we'll solve these. So x is greater than 6, and over here, x is less than negative 2. All right, so for this part, less than negative 2, it's strictly less than, so use the parenthesis. And over here, greater than 6, 6 to infinity. So some of these will have a little bit more complex expressions inside there. But it's going to work the same way. We got the absolute value part is less than or equal to the number. So this is an and inequality. So we'll take the opposite, put it over here, negative 7, less than or equal to 2x plus 3, less than or equal to 7. Make sure these always face the same way. Should be the same way as up here. All right, now solving this, you got minus 3 both sides, So that's negative 10 less than or equal to 2x less than or equal to 4. Now I'll divide all three sides by 2, and you get negative 5 less than or equal to x less than or equal to 2. So interval notation, since we have less than or equal to, we use the bracket, negative 5 to 2, and then the graph, brackets, and everything between. Your turn, number 3. Absolute value of 3x plus 5 less than 4. Absolute value is less than the number, so that is a and inequality. So we'll take the opposite, put it on the left, less than 3x plus 5 less than 4. Solving, we subtract 5 from all three sides. We've got negative 9 less than 3x less than negative 1. Divide everything by 3, and we get negative 3 less than x less than negative 1/3. All right, there's interval notation. Parentheses because we have strictly less than. Same symbols on the graph. And all numbers between. All right, we have to be careful on the next one. We got absolute value of 5 minus x is less than 2. The absolute value is less than the number, so this is an and inequality. Got negative 2 less than 5 minus x less than 2. All right, solving. Get rid of the 5, minus 5, minus 5, minus 5. So we got negative 7 less than. Now, what do we bring down the middle? X? No, we didn't get rid of that negative. It's negative x in the middle. Big difference. Because now we're going to have to divide all three sides by negative 1. So we get 7 here. And now, don't forget to switch the direction of the inequality. Whenever you multiply or divide by a negative, you've got to switch that direction. So this will be all numbers between 3 and 7. So 3 and 7, remember in interval form, smaller number goes first. So make sure you bring that one over here. And the graph, 3, 7, same symbols, parentheses, and everything between. And that brings us to your turn, number 4. All right, we got absolute value, which is less than or equal to 1, so that is an and inequality. So bring the 1 over here, make it negative. Less than or equal to negative 7 minus 4x, less than or equal to 1. So here's the inequality we need to solve. I'm going to get rid of that negative 7, so I'm going to add 7 to all three parts. So that gives us 6, less than or equal to negative 4x, less than or equal to 8. All right, now we've got to get rid of the negative 4. So divide all three sides by negative 4. And since we're dividing by a negative, we're going to switch the direction of the inequality. All right, so this turns into, see, 6/4 reduces to 3 halves. So we're going to have negative 3 halves there. Switch the direction on the sign. X in the middle. Switch the direction there. And 8 divided by negative 4 is negative 2. So that gives us, brackets here, since we have less than or equal to, -2 to -3 halves. And on the graph, we got -2, -3 halves, brackets for the symbols, and everything in between. Now, all the ones we've seen so far have had the absolute value isolated from the very start. But that doesn't always happen. So make sure first thing you always do is isolate the absolute value, both for inequalities and equations, because these techniques will not work if you don't isolate it first. So example, we got 2 times the absolute value of x minus 1 is greater than or equal to 6. So first thing we're going to do before we do anything is divide both sides by 2. That gives us x minus 1 is greater than or equal to 3. All right, now we've got an absolute value which is greater than the number, so this is an OR inequality. So x minus 1 greater than or equal to 3, or x minus 1 less than or equal to, switch the sign, and opposite of the number. Biggest mistake I see on those is not switching the sign on the second equation. Make sure you do that. X greater than or equal to 4, or x less than or equal to -2. Alright, so this part, less than or equal to -2, that will be -infinity to -2 for the bracket, union, and then this part, bracket 4 to infinity. And on the graph, that looks like, got the brackets going opposite directions. Your turn, number 5. So let's isolate the absolute value first. We're going to get rid of that 3. Subtract it from both sides, and we get x plus 5 is greater than 5. All right, we got an absolute value greater than the number. So that is an OR inequality. X plus 5 greater than 5, or x plus 5 less than -5. All right, now we'll solve these. Subtract 5 from both sides, we get x greater than 0, or x less than -10. So we have strictly less than, so there'll be parentheses. So, -infinity to -10, union 0 to infinity. Now there's some special cases of absolute value functions we should keep in mind. Should say absolute value inequalities, said equation. That's a misprint. Okay, so what if you have an absolute value that's greater than some negative number? Well, absolute values are always positive. It doesn't matter what number we plug in here. I could plug in -1 billion, and it's still going to be positive, so 1 billion is greater than -3. So it doesn't matter what we plug in here, it's always true, so the solution to this is always all real numbers. Negative infinity to positive infinity. All right, next up, x minus 4 is less than negative 8. Absolute values are always positive, so they cannot possibly be less than negative 8. So if you ever have an absolute value that is less than a negative number, the only solution is the empty set. No solution at all. All right, C. What if we have absolute value less than or equal to 0? Okay, well there's two different possibilities here. It could be less than 0, in which case it's negative. But absolute values can't be negative. So that part doesn't make any sense. But it could equal 0. So that's the only thing we have to solve then. Just translate this directly into x minus 4 equals 0, and that's x equals 4. Your turn, number 6. First one, always start by isolating the absolute value. It's hard to see which situation it is unless you get it alone. So subtract 7 from both sides. That gives us 2x minus 3, absolute value, less than or equal to 0. All right, so this is like example part C. We have less than or equal to 0. It can't be negative, so the less than 0 part doesn't make sense. So we'll only have to worry about the equal to 0 part. So 2x minus 3 equals 0. We'll solve this and get x equals 3 halves. All right, this one, to get the absolute value by itself, we'll subtract 10 from each side and get absolute value of x greater than or equal to negative 6. Well, absolute values are always positive, so any number we plug in here will satisfy that. So that gives us all real numbers, negative infinity to positive infinity. And over here, subtract 3 from both sides, that gives us x plus 2, absolute value less than negative 2. So absolute values can't be negative, so they can't possibly be less than negative 2, so that one is the empty set. So our last topic is the idea of relative error or tolerance. So let's say we're creating a piston for an engine. That piston has an ideal size, but it's impossible to make a piston exactly the right size. But as long as it's close, it's going to work. Now, if it's way too big, it's not going to fit. And if it's way too small, we're going to be leaking oil all over the place. But as long as it's very close, it works. And that's the idea of tolerance. How close do we have to be to that absolute perfect value for something to work? So let's say we take our temperature, we get a reading of 99.1 degrees Fahrenheit, which is higher than the average temperature of 98.2. So is this normal, or are we sick? So the idea of relative error will help us answer this question. in the equation, x minus x sub t over x sub t equals relative error in x. All right, so this is how we would calculate the value in a certain situation of a relative error. So in this situation, we know that the ideal temperature is 98.2. So we're going to put that in for x sub t. X sub t is that ideal value that we're shooting for. So it'd be that perfect size of the piston. And x is what we're going to solve for. So we got 98.2. We'll plug that in for x sub t. And now, problem says body temperature should be within 1.1% of the average body temperature should be considered normal. Now, relative error, this is expressed as a percent, and when we plug it in the formula, we convert it to a decimal. So relative means it's relative to the size of the object. So it's expressed as a percent of that ideal size. Now, when we calculate the relative error for this situation, we want it to be less than or equal to 1.1%. We'll convert 1.1% to a decimal. So take the decimal, move it 2 to the left, and we get 0.011. So we need this quantity here to be less than 0.011. All right, so we're going to solve this. We have an absolute value that's less than or equal to the number. So this is an AND inequality. Alright, so there's our AND inequality we're going to solve. So we're going to start off by multiplying everything by 98.2. And that'll get rid of the denominator in the middle part. So it gives us negative 1.08 less than or equal to x minus 98.2 less than or equal to 1.08. All right, now we're going to, last step, add 98.2 to all three sides. And this gives us our range of normal temperatures within 1.1% of the ideal temperature, 98.2. So any temperature between 97.12 and 99.28 is considered a normal temperature. And the temperature we were given was 99.1. So that's within this range, so it's a normal temperature. And just make sure you see the note. These values are approximate and should not be used to diagnose actual disease. Okay, we're back to the introduction. What's the range of acceptable weights for a 20-ounce box of breakfast cereal if the actual weight must be within 3% of the printed weight? All right, our ideal weight is 20 ounces, so we'll put in 20 for x sub t. And we want this relative error that we're calculating here to be less than 3%, or 0.03. So just like before, we've got an AND inequality, because the absolute value is less than the number. So we'll do negative 0.03 less than or equal to x minus 20 over 20 less than or equal to 0.03. All right, let's get rid of that denominator. Multiply all three parts by 20. And that gives us 0.6 less than or equal to x minus 20 less than or equal to 0.6. Plus 20. And And that gives us 19.4 less than or equal to x less than or equal to 20.6. Alright, so that means if the box of cereal has between 19.4 ounces and 20.6 ounces, then it is within 3% of what's printed on the box. And that's it for today, everyone. And that wraps up Unit 1.